In this video, we're going to try to go back through the Voltaic cells. They're really an important concept. Being able to label them is extremely important, as well as being able to take them apart and figure out what goes on. So in this video, we're going to go back over the zinc copper cell. There's another video that explains this as well, but I wanted to kind of connect it to your notes. So we've looked at the cells, and whenever we're looking at these cells, we got to look at what's going on in the, or what the reactants possibly are in the products. And so in the cell that we've got here, we've got copper electrode in copper 2 sulfate solution. So this solution down here is going to have some sulfates in it as well. And then we've got zinc sulfate solution, so it also has sulfates, or if it was zinc nitrate, they're both going to be spectators in this case. So if I've got all of those things, I need to find the entities in solution. My waters are here. I have copper ions as well as copper solid, zinc ions, and zinc solid. If you're making an actual cell, you might not include necessarily all of these reactants, because you can see that my strongest oxidizing agent is going to be copper 2. So I would want copper 2 present because it's a reactant, but I don't need to have copper be the chemical that is at the cathode. It could be just a piece of carbon, because the copper is going to plate there. So sort of whatever's cheaper and less toxic is what we would choose. The zinc metal, though, I would need to have, because zinc metal is my strongest reducing agent. And so the zinc metal is going to become zinc ion. The cell looks kind of like this. So I've written out the two half reactions, and my cathode is going to be my carbon, it's positive, and my anode is going to be my negative electrode where the zinc is. And you'll see that the electrons are traveling from the anode. That's where they're lost, right? And so their electrons are going to travel in the exterior circuit to the copper electrode. And in any of these cells, we're going to have the cations will go to the cathode, and the anions will go to the anode in the saltwater bridge. So this is my saltwater bridge, and it just allows the ions to travel, and it separates the two half reactions so that the ions need to travel through the saltwater bridge, but it forces the electrons to travel through the external circuit. Now, something that we haven't gone over yet is that we can calculate the voltage of this. So the voltage is going to be called E cell. So the electrical potential is what this counts for. And the electrical potential for any cell is going to be the cathode minus the anode. And so off of this table, I can calculate the E cell by taking the cathode, which is the copper, and its voltage is positive 0.34 volts. And my zinc down here is negative 0.6, so minus negative 0.76 volts. And this is going to give me a positive 1.10 volts. Now, spontaneous reactions always have a positive voltage. If you have a negative voltage, it indicates that it's a non-spontaneous reaction. Voltaic cells are always spontaneous. I want to just go then back to your notes briefly and point this out. So it says calculating electric potential, that's here. You can, here it says E net, or that's what I would have as your E cell, equals E reduction. Well, that's the cathode, right? So we know that GrOA cathode, and then minus the E anode. And my anode is going to be Leo Ra. That's my anode. So this is saying the exact same thing. I like to frame it in terms of anode and cathode instead of just talking about what's reduced and what's oxidized. The cell potential here says it's got this little like naught symbol. That means under standard conditions. So the standard conditions are like 1 mole per liter and at SATP. This is a confusing concept for a lot of people. So what is the standard cell potential? And the standard cell potential is basically all of these voltaic or these half reaction voltages are figured out using the hydrogen half reaction. So at 0.0, this is called my reference cell. So this is my reference cell, and its voltage is 0.00. That was just chosen. So essentially what they do is, if they wanted to know what the silver potential is, they go E cell equals E cath minus E anode, and my cell potential is going to be measured, so they experimentally, they have this is the anode and this is the cathode. And so it's going to be positive 0.80 volts minus 0.00 volts is 0.80 volts. And that's how they determine this number. They use the hydrogen as the anode, and they set up the cell and then measure the voltage for everything. So if they had hydrogen and nickel 2 and they set that cell up, the E cell in this case, the cathode would be the nickel, will be minus 0.26 volts minus 0.00 volts. So the E cell is minus 0.26 volts, and that's how they get to this number. Well, the reference cell here is a decision. Somebody decided at one point that we're going to make those the reference cell. We're going to say that's the reference cell. But kind of an interesting understanding and a bit of a thought experiment is, what if we change the reference cell? Well, if I made instead, cobalt with the cobalt 2 as my reference cell, this would be my anode, and everything else's voltage would shift, right? We'd move where 0 is from being here, and now this would become 0. So all these numbers would shift by 0.28 volts. Every number would get bigger by 0.28 volts. And if we were to calculate what the new half reaction cell potential is, so let's say we were going to calculate copper with a new reference cell, and we said that that was going to be my nickel. So if nickel now is 0.00 volts, if that's what this value is, then what will the value for copper be? What should that number here be now? Well, all I need to do is calculate the E cell equals the copper compared to the nickel. And so E cath minus E anode equals positive 0.34 volts minus negative 0.28 volts. And my new value is going to be 0.062 volts. And so this number would no longer be 0.34, it's 0.62 volts. It's a positive value because this number is now 0. So if this is 0.00 volts, the difference between them is exactly the same. So the cell would have the same overall voltage, but now this becomes 0 by changing and making it the new reference cell. So questions about reference cells can sometimes be confusing. If they ask about what's the new cell potential for a half reaction, you just calculate it like that. If they say, oh, we've changed the reference cell and I've got bromine and I've got cadmium, what's the cell potential? Well, the cell potential is still just the difference between those two things. Just like here, the difference between the copper 2 ion and nickel are exactly the same amount difference, but if this is my reference cell, which means that becomes 0.00, this now is positive 0.62 volts. I'm guessing you will need to rewatch this. Please try to rewatch this and make sense out of it. The time when the reference cell makes a difference is the reference cell, if I changed it to become, this becomes the new reference cell, every number changes because now this becomes 0.00 volts And the way they calculate what those new numbers are is by doing this calculation, and now my anode is 0.00 volts after you've calculated it, right? So that the cathode value will be the same as the E cell. There will be questions like this that people ask. They will be in the textbook. They are frequent on the diploma, and they are frequent on unit tests. So not like 1,000 of them, but it almost always shows up on the diploma. Do you understand the reference cell, and do you understand how these half cell voltages are shown?